In this video, we want to summarize what happens for repeated roots when we use reduction of order. Let's assume that we have a second order linear constant coefficient equation of the following form: a y double prime plus b y prime plus c y equals 0, and we have a repeated root. This means that the quadratic ar squared plus br plus c factors as r minus what I'll call r0 squared and then times a. So if we assume that a is 1, which we can get through by dividing through by a, we can then get that this equation reduces to y double prime minus 2r0 y prime plus r0 squared y equals 0, because then when I get to the coefficients, I'll get exactly r minus r0 quantity squared. Now from this, we know from the outset, by our standard approach of guessing e to the rt and solving, that y1 of t is e to the r0t is a solution. Let's use reduction of order to try to find a second solution. So using reduction of order, we're going to plug in v of t times e to the r0t for y. With this, we have that y prime is a product rule, like so. We get a v prime when the derivative falls on the v, and I get an r0 when the derivative falls on the exponential term, and I can find the second derivative in the same way. Or collecting terms, the second derivative is a v double prime times e to the r0t plus 2r0v prime e to the r0t plus an r0 squared v e to the r0t. And then I can plug all of these into my differential equation and see what I get for the solution. Since our equation was y double prime minus 2r0 y prime plus r0 squared y, when I plug in, I get the following, and this should equal 0. And now I want to simplify terms here. So we'll see that this term is 2r0 v prime e to the r0t. That's going to cancel out this term here once I distribute in the 2r0. I will also have a plus r0 squared v e to the r0t with another plus r0 squared v e to the r0t, and then minus 2 of that same term once I distributed that minus 2r0. So those will also all cancel out, leaving me with exactly one term, v double prime e to the r0t equals 0. And since e to the whatever is never 0, I can get rid of that, and I'm left with just v double prime equals 0. We saw with the earlier example, it works in any case we have a double root for a constant coefficient equation like this. But what's the solution here? The solution here then is just v of t is at plus b for some constants a and b. Two derivatives gets me 0, we're good to go. But we now gotta go back one step further. What is our solution to the entire equation? Our solution y was v of t times e to the r0t, or in this case, at plus b e to the r0t. And this works for any a and b. Now in this particular case, we know that b is sort of already accounted for with my y1 being just e to the r0t. So what I care about is this extra t that comes out here. So I can pick, for this case, a to be 1 and b to be 0 to get my y2 of t as t e to the r0t. And that will be the second solution that I get for this problem. So I'm left with two solutions here. I have y2 is t e to the r0t, along with my y1 being just e to the r0t. And both of these will solve the differential equation because that's how we define them. We have one last check to make, and that's that this is a general solution. And for that, we need our Wronskian, which, as you recall, is y1 y2 prime minus y1 prime y2, which in this case will be e to the r0t times the derivative of the second, which is a product rule, e to the r0t plus r0t e to the r0t, and then minus y1 prime is just r0 e to the r0t times t e to the r0t. We'll see this term and this term canceling out because they're the same with a minus sign. So I'm left with exactly e to the 2r0t, which is never 0. Therefore, these give rise to a general solution, giving us that our general solution in this particular case is going to be y of t is c1 e to the r0t plus c2 times t e to the r0t. So your second solution here comes by multiplying an extra t times the one that we already had. And then from here, you can use this with initial conditions to figure out what c1 and c2 have to be. That's what we always get for second order equations with repeated roots. We're always going to get e to the r0t and then a t e to the r0t for our second solution to these types of equations.